In this video, I would like to present the simplex method for linear programming models. And this method, of course, is used to solve optimization models that have linear objective, a set of linear constraints. And I'm going to show it to you on an example or a model that is put in a standard format where the objective is a maximization. C is the vector of objective coefficient, C transpose, CT stands for C transpose, times X. X is a vector of decision variables and subject to constraints A, matrix A of constraint coefficients multiplied by vector X equals the vector of right-hand sides B, and all the variables X are greater than or equal to 0. And this is a kind of graphical representation of the model that is written here on the left in a very short format. So basically this is the C transpose, right? All the vectors like X, all the vectors are assumed to be column vectors. So if I want a row vector, I need to transpose it. And of course the objective will take a scalar product, meaning that you take the first objective coefficient multiplied by the decision variable plus second coefficient times second decision variable plus and so on until the end. And then the constraints are the matrix A is a matrix of m rows and n columns, right? And the matrix is multiplied by vector of decision variables X, and it has to be equal to the vector of right-hand side values B. So we're assuming here equality. And of course, the way this is calculated, again, it is a sum of products of each row is multiplied by each column. In this case, there's only one column, a vector. So basically, we'll take the first constraint will be the first coefficient here multiplied by the first decision variable, and then plus second coefficient in the first row times the second variable plus so on, right? And equals to the first coefficient in the right-hand side. And then the vector X here is greater than or equal, right? Each variable is greater than or equal to 0. So how does the simplex method work? Well, first thing we need to do is we need to assume, we need to select, we're going to select m out of n variables x, right? So notice we will assume that the model that we have has m smaller or equal to n, which means basically that the number of rows in the matrix A is not higher than the number of columns in this matrix. And also we're going to assume that the rows in the matrix are linearly independent. So if we select this, we can actually call the selected variables, right, will be, right, selected, or let's put it for short, selected variables will be xb, right, and we'll call this basis or basic variables. And then we will also have the remaining variables xn will be non-basic variables, right? So what we can think about, I think we can think of it as right, the vector x is divided into those two sub-vectors. The problem here is that it's any subset of variables x can become xb. So for example, xb could contain second variable, third variable, fifth variable, 11th variable, and so on, right, as subset. Now, to represent this graphically, I will assume if I reorder those variables such that the first m will be the basic variables, right? So if I reorder them, I could present it like this. I could say this is xb, and this is x and the remaining, right? The xb has exactly the same number as m, right? Here you see the height of m. So this is the basic variables, right? And of course here the same, and here the same, right? So this is xb, and this is xb, and this is xn and xn, right? And of course, you know, if I want to rewrite this model, I could divide the cost coefficients, the objective coefficients, I could call them CB transposed and CN transposed, right? Of course, B's remain as they are, but also the matrix A can be divided into, right, the part that corresponds to the basic variables. I'm going to actually call it just B, not AB and AN. I could call it AB and AN, but I'll call it B and N, right? And so with this, I can reformulate this model, rewrite it slightly differently. I can say it's the same as maximize, and then instead of taking C transpose X, I'll just first take the CB transpose X, B, right? First the basic variables, and then Cn transpose times Xn, right? So this is the same calculations, the same model, just I broke down the products into a sum of two products, right? And then the same thing, the constraints A times X will be B times XB plus N times XN, right? So subject to B times XB plus N times Xn will be equal to the right-hand side remain as before, B. And then, of course, I could say here x greater than or equal to 0, but remember x includes the xb and xn variables, so all of them, right? Maybe actually let me break this down. xb greater than or equal to 0, right? xb, and the same thing, xn greater than or equal to 0, right? So this is important to realize. We had a model that was in this format, right? And we rewrote it in this format, right? But notice it is the same model, just I basically played around with the symbols. I have a different looking model, but actually it's the same as the original one, right? So we will also say what we call B here and what we call N are B are called basic columns, right? Basic columns, right? It's the set of M columns that correspond to basic variables, and N, of course, will be right, the remaining, so we could say non-basic columns, right? As similarly, of course, we split vector C, right, into CB and CN, right? So I'm not going to write these details just to save time and space, right? And so this is a visualization. And remember, this visualization assumes I reordered the decision variables and the columns and the cost coefficients such that the first M out of N are the variables that we selected as bases or the columns that we selected as basic columns. Right? So this is the first step. The second step, now assume that the basic columns, the B, is an invertible matrix. So we're going to assume, right, B minus 1 exists. So I want you to see, of course, B had originally, right, the A matrix had originally M rows and N, which was more than M columns. Right, but B is M by M. It's a square matrix, right? So B a square matrix can have an inverse, but not every square matrix have an inverse, right? So we're assuming in this case B, the inverse exists. So that means, of course, that if you multiply B minus 1 times B, you get an identity matrix, right? Which is something like 1, 1 on the diagonal, and everything else is 0, right? So we're assuming this B minus 1 exists. Now, if it exists, I can actually rewrite the constraints. I can write the constraints. How can I modify them, right? I can take the constraints and say, let's multiply both sides by the B minus 1. So I'll have B minus 1 times B xb plus b minus 1 times n xn, and right equals b minus 1 times right hand side's b, right? And of course this I can rewrite a little bit more. I can say, right, of course this now is the identity matrix that I defined here. So an identity matrix times vector xb, it will just be xb, and this I can take to the right hand side, so I can say b minus 1, b minus b minus 1 n xn, right? So it's interesting that if the inverse of b exists, we can express variables, right? Notice we can express xb as a function of xn, right? So all the xn variables are on the right-hand side, and if I assumed some values for xn, I could actually calculate values of xb, right? So also I can use this information and say, let me now eliminate various variables xb from the objective, right? So I'll take the objective and as well rewrite it, right? So the objective will be now maximization, and right, CB transpose times, and instead of xb, I'm going to substitute what I see here in the constraints. I'm going to say b minus 1, small b minus b minus 1 n xn, right? And then the remaining part plus cn transposed xn. So notice that here we only have xn now, right? Of course, we substitute for xb, and now I want to reorder those terms slightly. So I want to write first what's without xn, that's cb transposed b minus 1 small b, and then the rest is with xn, and I'm going to start with this part, so I'm going to say plus cn transposed times xn, of course, right? But I'm going to leave xn a little bit further, and minus this minus, and then we take cb transpose times b minus 1 times n, so it's cb transposed times b minus 1 times n, and all of it is multiplied by xn, right? So this is again xn, right? So with this, I can rewrite my original model as follows. I can say now my model is maximize, right? Maximize this objective, so it's C B transposed B minus 1 small b, one second. I'm going to actually write it with slightly different color here. C B transposed times b minus 1 and times small b minus 1 times small b in black. I'm just trying to emphasize here something. Plus, and there's one more thing I want to do here. This part, I'm going to replace it with a new symbol called C n bar transposed, right? I'm going to replace it with this. So, right, it's just a set of parameters, no decision variables here, right? So this is going to be called C n bar transposed multiplied by x n, right? And let me scroll this a little bit. Okay, and then subject to, and the constraints. What are the constraints? We rewrote them as you can see here, right? xb equals b minus 1 small b minus b minus 1 and xn, right? So, and then of course I need to keep xb greater than or equal to 0, and also xn greater than or equal to 0, right? So notice, right, again, we rewrote the model that was originally in a slightly different format, but this is the same model, well, with a few more assumptions, with an assumption that, right, we chose this set of basic variables such that the b minus 1, the inverse of the basic, of the basis, of the basic set of columns, the inverse of b exists, right? So now that we've created this, I want to observe something. First of all, what is this part CB transpose B minus 1? Well, we actually call this, right, so CB transposed B minus 1, this is what we call shadow prices. And these are actually like values of constraints. So they multiply each shadow price multiplies the right-hand side of the constraint, and it gives us some kind of value for the objective by multiplying the available right-hand side values, like available resources units are multiplied by a price of the resource, right? And notice that actually those shadow prices also occur here, right? They are here as well, slightly. Maybe I'll highlight it. Right? The shadow price is also here, right? CB transpose B minus 1. And what is this Cn transpose? So this is Cn bar transposed are actually reduced costs, right? And of course they depend, right? Why are they called reduced costs? Because we take original cost coefficients and we reduce them by the values related to shadow prices. So we can actually write this here, right? So we will say CB, let me actually use different fonts. So this is equal to the original Cn transpose, the original, minus, and now I'll use the green to emphasize, these are the shadow prices, CB transpose B minus 1 times N, right? So reduced costs are original costs reduced by some values related to shadow prices. Okay, so why is this interesting? Well, because we can now, with this formulation, we can define basic solution. A basic solution is a solution that sets all xn equal to 0 and then calculates xb using the constraints. So we will define basic solution. Basic solution, right, is going to be what? It's going to be something with xn, make them equal to 0. So what I want you to see is, if you put xn equal to 0, basically this term disappears and this term disappears, and all you have is the objective value is exactly equal to the value of resources at shadow prices, this part, and xb's are equal to just this product, the b inverse times the number of resources b, small letter b, right? So we can say that in this case xb equals b minus 1 multiplied by b. Of course it depends on xn, but now xn is 0, this part disappears, right? And then we can say also that objective value is, and I'm going again to use green color to emphasize these are the shadow prices, CB transposed B minus 1 times small b, right? So this is the basic solution. Why is it interesting? Well, it will be interesting if it's feasible. How can it be infeasible? Well, first of all, the constraints are already satisfied, the first line of constraints, right? Because we calculated xb using the constraints, assuming xn is 0, right? All xn are 0. However, we have these restrictions, and notice xn greater than or equal to 0 is satisfied, but xb greater than or equal to 0 doesn't have to be satisfied. It's possible that, that xb could be negative, or some of those variables, and xb could be negative, right? So we could say if xb, all of them are greater than or equal to 0, then this is called, we have what we call a basic feasible solution, right? Let's call it BFS for short, right? So basic feasible solutions actually correspond to corner points in the graphical method. Remember when we had corner points in the feasible region? Each of those corner points is one of the basic feasible solutions, right? It has some variables zeroed and the other variables calculated according to the constraints, right? And it defines, right? So infeasible basic solution would be if you extend this, for example. So this is the feasible, right? If you extend this a little bit further, these two constraints, and find an intersection of those two constraints, but this constraint, right, which says below the line, is not satisfying. This is a basic solution, but it would be infeasible. It wouldn't be, it wouldn't satisfy all the non-negativity constraints, right? So let me clean up this a little bit. So why, how do we proceed with this? Well, we could actually think about generating all basic feasible solutions, right? If I generate all basic feasible solutions, the theory tells us we could find an optimal solution just by finding the best of them. However, the number of all basic solutions is actually n over m. So it's a very large number, right? This is n factorial divided by m factorial multiplied by n minus m factorial. That's a very large number. Like if you take, let's say, n 100 and m 50, oops, not divide, but over 50, right? That's number of combinations of 50 out of 100. This is about 10 to the power of 29. So there's a very large number, and it's basically practically impossible to solve a problem like this by just enumerating all basic solutions and then finding which ones are feasible and then finding which of them is the best. So how can we solve, right, with this knowledge that we have here, how can we solve the problem, the linear programming model, a little bit better, right? So what we're going to do here is we're going to ask ourselves, if we have one basic feasible solution, right? If this xb, I selected xb, right? And I have one basic feasible solution. Can I find another one? And hopefully, can I find a better one, right? So what we can do is, right, we'll ask ourselves, how can we find a different, right? How can we find a different basic feasible solution? How can we find one? Well, we can find it by doing this. We can say keep all variables in xn at 0, right? So basically, right, remember xn is equal to 0. So let's keep them all equal to 0 except one, except for one. Say we call it, right, we call it some variable xj, right? So it's one of those variables, right, that we will increase, right? We will increase it, right? So we're increasing xj. Remember, xj is here, and it's somewhere here. So it's going to change the objective value, and it's going to also change xb values. And in fact, because it's a matrix here that multiplies all xn variables, xj is going to affect every xb variables, right? So all xb variables. So basically what we can say is as this xj increases, right, all xb may be changing or might be changing, right? All of them might be changing. Now, how are they going to be changing? According to the constraints, right? According to this constraint. So they could be decreasing or increasing, or they can stay the same, right? The same, unchanged. Right? So it depends. So basically, you know, if you think about all of those variables inside xb, each of those variables, I don't know, let's call it, right, xb1, will somehow depend, there will be a constant that comes from this first term here, and there will be minus or plus some value times this xj that we're increasing, right? And depends on whether this is minus something or plus something, or it is just 0 times xj, right? So each of those variables, and b1, b2, b3, and so on, each of them may be increasing, decreasing, or staying the same, right? So now consider only those variables that decrease, right? One of those variables is going to reach 0 at some point, right? So if there is a set of variables that are decreasing, these are the interesting ones, right? Right? This is interesting. Interesting. Right? Why? Because when they decrease, if they decrease, become negative, they could violate our feasibility conditions, right? As long as they stay positive or 0, they're fine. So consider that let's call this xk, right, small k, be the variable in xb that achieves or decreases to 0 first, right? So think about, you know, these variables are changing, some of them are decreasing, and those out of those that are decreasing, xk is the variable that decreases to 0 first. But if it decreases to 0, we could now call this variable a non-basic variable, because remember, non-basic variables are 0. And since we increased xj, which was one of the xn variables, now we have to move it to xb as basic variable, right? Because it's no longer 0, right? So we can say we obtain, right, a new basis by an operation which is called pivoting. 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 And pivoting is what it is. Let's underline this. Pivoting is as creating new bases, a new basis, right, by removing or adding first, right? We add xj to xb and removing xk, right? So again, consider this. We started with some bases and some variables were non-basic. Non-basic variables were 0. We took one of those non-basic variables, right? This was the xj, and we increased it. So it cannot be a non-basic variable, it has to be a basic variable. So now xj, we added it to xb, right? New basis xb, right, has now xj in it. But it cannot have m, it would have now m plus 1 variables. It has to have just m variables. Remember, xb is selected m variables out of all x variables, right, which were n. So we have to remove something. So we increase this xj until one of the original xb variables decreases to 0. And this variable that decreased to 0 was this xk. And this one we then remove from the basic variable. So we put it into xn, right? So why is this interesting? Because notice xb is now a different basis, and that means it corresponds to a different basic feasible solution, right? And maybe it's a better solution. When would it be better? Right? So the question, will new basic feasible solution be better than the old one? The old basic feasible solution, right? And what's the answer to this? Yes, if right, before pivoting, variable that we chose, xj, to put in the basis, right, to add to the basis, had reduced cost, right, reduced cost cj bar. This reduced cost, right, one of those numbers that corresponds to variable xj, is cj bar, had it greater than 0, right? Why is this? Because consider this, in the objective has this value, right? And then this was all 0, so this was also, the whole part was 0, right? But now that we increase xj, xj is multiplied by the reduced cost cj. If this cj is positive, increasing xj will result in an increase of the objective function value. So therefore, we will have an improvement of the objective function value. Maximization will be improved as we increase this xj, right? And so that means, but there's actually one more condition I should add here, and after pivoting, the new value of xj is more than 0, right? So after pivoting, I have to, like, there are some degenerate cases where actually pivoting results in no increase of xj, but I'm not going to discuss them in this video, right? So provided that we have a positive reduced cost, we can find a better basic feasible solution. So actually, this leads us to the algorithm for the simplex method, right? The simplex method can be written as follows. It will have, right, the simplex method will be what? We'll have 2 stages. Stage 1, right? Stage 1 of the simplex method is find initial basic feasible solution. Actually, I didn't say how to do this, right? But we need a starting basic feasible solution. If we have it, right, then we do stage 2, right? And in the stage 2, we try to do what? We try to find, use pivoting, right, to find a better basic feasible solution, right? So we could say improve basic feasible solution, right? The current basic feasible solution using pivoting. Right? So this is a little bit brief, but let's be more specific here. So first of all, what do we need to see? We need to see if all xn variables, let's look at their reduced cost. We'll have the problem in this format. Let's look at all those reduced costs here that stand in front of the non-basic variables at the current basic feasible solution. If any of them is positive, that means increasing a non-basic variable will lead to an improvement of the objective. So this is the first thing. We can select this xj as the variable that will enter the basis. Then we can identify the variable xk that will leave the basis, right? And if we find this variable, we will then be able to find a new basic feasible solution, right? And we can apply pivoting, right? So more specifically, we can say in stage 2, I'm going to scroll it a little bit and say, what? In stage 2, we will, let's actually put a detail here. So in stage 1, first of all, if it's not possible, right? If it's not possible to find this basic feasible solution, then the problem is infeasible. Right? Problem is infeasible when you can't find any basic feasible solutions, like you don't have a single feasible solution. So the problem is called infeasible, and we can stop the method, right? If and in stage 2, what do we do? How do we do this improvement? First, we check. So this is stage 2. Check. Let's actually put this. Check optimality condition. Optimality condition is all reduced costs, right? Those C and transpose C and bar transpose less than or equal 0, right? Actually, I don't need to transpose them, but right? If this is, all of them are less than or equal to 0, that means the improvement is not possible. If, right? So I could say actually, if all those reduced costs are less than or equal to 0, then we have an optimal solution found, right? So we have the case where we have an optimal solution, right? Otherwise, there must be a variable with at least one variable with a positive reduced cost. So if this is not satisfied, right, then we can say select xj from xn with the reduced cost that is greater than 0, right? And this is going to give us, right, because we said earlier, this will improve the feasible, the basic feasible solution, right? So we select xj, right? Then we identify xk in xb, right? That will be the first to decrease to 0, right? That will be the first to decrease to 0 as xj increases, right? And now finally we apply pivoting, and repeat the stage 2, right? So basically these are the steps. And what is interesting also, when we identify xk in xb, that will be the first to decrease to 0, right? If this is not possible, what do I mean by this? If xb, if you look at all the basic variables, and none of them decreases when xj is increased. So some xb stay constant, and some variables in xb, they increase, right? Then what that means is that xj can be increased to infinity, and we will still have a feasible solution, right? And in that case, and remember, the reduced cost indicates that as we increase xj, we increase the objective function value. So that means we can increase the objective function value without limit, right? If this is the case, then the problem is unbounded. Right? This is the case where the problem is unbounded, and I hope you can see now that the simplex method can find in the first stage the problem might be infeasible if no basic feasible solution can be identified, and in the second stage, if after some steps, after some iterations of the simplex method, we find that all reduced costs are negative or 0, we have an optimal solution. And if we do some iterations and at some point we find out, yes, there is an improvement possible, but no basic variable decreases to 0 as we introduce variable xj into the basis, then we have an unbounded problem. So we have the 3 cases.